Welcome back, fellow mathematicians. Um, in our last video, we journeyed through the construction of the coarseness topology, a concept that actually ensures smooth transitions between the collection of maps. We discovered the elegance of defining the simplest set of rules, allowing these maps to transition seamlessly without any abrupt changes. But guess what? Our exploration doesn't end here. It is just the beginning of a fascinating journey into the depth of topology. So today we are going to talk about weak topology, right? Just as the coarseness topology provided the foundation for continuity of a collection of maps, the concept of weak topology actually takes us even further by introducing I would say, a new layer of flexibility and insight. Just think of it as a delicate dance, delicate dance between maps and their dual space. So where continuity is actually measured in a remarkably subtle manner. So what the coarseness topology actually say ensured transition without disturbances. Weak topology actually, refines our understanding by allowing us to capture convergence, boundedness, and continuity in a nuanced way. So it's like uncovering hidden patterns, within the smooth flow of our maps, revealing intricate connections that might have gone, say, unnoticed before. So, as we dive into the world of big topology, I would like you to remember the journey we began with the coarseness topology. Um, so we will start right away with, so let E be a Banach space. Oops, we have another column. So let E be a Banach space. And let F an element of the joule. So, and then we define the function phi f, right? Defined from E to R by phi f of x equal f of x. So as f runs through the dual space, of E, we obtain a collection of map, say phi f in the dual space of E. So we now, from now on, we will ignore the usual topology on E, right? But usual topology, the topology induced by the norm, right? And we define a new topology on the set E as follows. So definition. So the weak topology sigma E is star. Maybe a new column. So the weak topology. The weak topology sigma E star is the coarseness topology associated to the collection phi f in E star, right? In the sense of, for those who watch my video on the coarseness topology, so I will just put in bracket, so in the sense of of I think it was of part 5, I guess so, of part 5, with x equal e, yi equals r for every I, right? And capital I equals to the dual space, right? Because I mean, we actually, we had in the last video the set X that was without any structure and the collection of topological spaces yi, right? And then we wanted to, we also had the collection of map phi I, and then we wanted to construct on X the cheapest topology for which that collection of maps um, um, is continuous. So that was just for the recall. Okay, so note that, every map phi f is continuous for the strong topology. And for the usual topology. And therefore, the weak topology is weaker than the usual topology. Okay, in fact, this is due to the fact that, every open set for the weak topology is actually open for the strong topology, for the usual topology. Okay, so we can state our first proposition 3.3. The weak topology, sigma E star, is actually Hausdorff. The weak topology sigma E star is Hausdorff. So what does it mean? It means that if you give me two distant points, I can find, two disjoint neighborhood of those points. Proof. So given, say given x1, x2 in E, right, with x1 different from x2, right? So let me put it another color. We have to find two open sets, say O1 and O2, right? Open for the weak topology. We need to precise that for the weak topology. Oops, it looks so ugly. For the weak topology, sigma E star, right? Such that put it in column. X1 is an element of O1, X2 belongs to O2, and O1 and O2 are disjoint. Then we call this star. Okay, so since x1 and x2 are actually, elements of a Banach space and they are distant, so we can actually apply the Hahn-Banach second geometric form. So by Hahn-Banach theorem, by Hahn-Banach second geometric form, there exists a closed hyperplane strictly separating x1 and x2. So this means that there exists a linear bounded operator f. There exists a constant alpha in R such that f of x1 is strictly less than alpha, which is strictly less than f of, I think using the dual pairing might looks a bit confusing, so let me just make it properly. F of x1 is strictly less than alpha, strictly less than f of x2. Okay, so now put O1, say put O1 to be the set of x in E such that f of x is strictly less than alpha, right? And O2 set of x in E such that f of x is strictly greater than alpha. So that means, so let me just rewrite O1 and O2. So you have O1, which can be written as the preimage of phi f minus 1 of minus infinity alpha, and O2 is phi f minus 1 of alpha plus infinity. So clearly, we can say that clearly O1 and O2 are disjoint, are open first, right? As preimage of open set via a continuous map. O1 and O2 are open for the weak topology sigma E star, right? And they obviously satisfy star. Good. And this ends the proof. Okay. So now let's try to characterize, neighborhood of element of the set E. So proposition 3.4. So let x0 be an element of E, right? Given epsilon positive, right? And a finite set of linear bounded operator, finite set of, say, finite set of f1, f2, Fk is a subset of E star, and let me just highlight finite, which is important. So that x0 in A, epsilon positive, strictly greater than 0, and you find a set of linear bounded, finite family of linear bounded operator. Now consider V, the set V, right? That obviously depends on the finite family of linear bounded operator as well as epsilon. So this is defined to be the set of x in E, such that the absolute value of the Joule pairing of Fi at x minus x0 is strictly less than epsilon, right, for every I moving from 1 to k. Okay, so then V is actually a neighborhood of x0 for the weak topology. So then V is the neighborhood of x0 for the topology sigma E star. Moreover, we can even obtain a basis of neighborhood of x0 for the weak topology by varying epsilon k and also the family of linear bounded operator. So let me iterate. Moreover, we obtain a basis of neighborhood of x0, right, for the weak topology by varying another color by B use blue one. So by varying epsilon k and the Fi in the Joule space. Okay, let's have a proof. Take a look at the proof. So clearly, clearly V is, can be written as the finite intersection of Fi minus 1 of the interval AI minus epsilon, AI plus epsilon, AI plus epsilon. So V equals to that with AI, which is nothing less than the Joule pairing of Fi with x0. So V is open, right? It's open for the topology sigma E star. It's actually open because we have a finite intersection of open set for the weak topology, and V contains an x0 belong to V. So therefore V is a neighborhood. You squeeze it here. Good. It's a neighborhood of x0. Well, I mean, it's easy to see that x0 is actually into V because of, I mean, the Joule pairing, or f of x0 minus x0 absolute value is equal to 0, which is obviously strictly less than epsilon. Okay, now let's try to show that, I mean, by varying epsilon and the finite family of the Fi's, we even obtain a basis of neighborhood. But first of all, let me remind you of something. Well, put it in bracket. So remember that a collection, right? A collection, we call it calligraphic F. A collection F of open sets containing x0 is a basis of neighborhood. It's a basis of neighborhoods of x0 if and only if let me first highlight the basis of neighborhood if and only if every open set containing x0 contains an element of the collection F, contains an element of F. So that was just a recall, right? But what we mean by basis of neighborhood. So now let's try to prove our claim. So let U be a neighborhood of. So let U be a neighborhood of x0 for the weak topology. So we know that, I mean, we know from section 3.1. By section 3.1, I mean our lecture on the coarseness topology, right? So we know from section 3.1 that there exists an open set, say W, containing x0, right? Such that W is a subset of U, and W is of the form containing x0, W containing F, and W of the form can be written as finite intersection of preimage of phi Fi minus 1 of Wi, where Wi is actually is a neighborhood. It's a neighborhood. We write it here in R of AI that I define above to be a Joule pairing of fi and x0. So since w is actually a neighborhood in R, we know how to, and since wi is actually a neighborhood of AI, it's a neighborhood in R of AI, we know how to kind of characterize neighborhood in R. So this means there is this, can find an interval, right, around AI that is contained into wi. So there is this epsilon positive such that the open interval, let me write it here, AI minus epsilon, AI plus epsilon is contained into wi, and this holds for every I. So from this it follows that, follows that x0 is an element of V, right, which is contained into W, which is contained into U. So hence this family, right, the family of V depending on, right, such that K is an element, the natural number, right, epsilon positive, F1, Fk linear bounded operators. So this family is indeed the basis of neighborhood of x0, basis of neighborhoods of x0 for the weak topology. For the weak topology, sigma E star. Good, and this ends the proof. So just I think I went was a bit too fast somewhere here, right? But this is actually easy to see, right? So observe that, from this relation here, so this implies that, here you just need to take phi fi minus 1 on both sides, right? So if you take phi fi from both on both sides of the inclusion, you arrive at W. It's actually contained, because remember what is that even? Yeah, V was actually the intersection, right, of the phi fi minus 1 of the AI minus epsilon, AI plus epsilon here. So from here, if you take, phi fi minus 1 on both sides, so, and then since the inclusion holds for every I, that means the intersection of, that V is actually contained into W. But W already is contained into U by, by definition of U being a neighborhood of x0. So good. So maybe I write it here. So this implies that the intersection of phi fi minus 1 of AI minus epsilon, AI plus epsilon, this is contained into W. I am moving from 1 to K, but this is nothing else. This is V. Okay, good. So just wanted to, to be a bit more precise. So, okay, let's have some notation first, right? So, notation. So if a sequence xn, if a sequence say xn, right, of element of E converges to X in the weak topology, sigma E star, then we shall write xn fancy arrow x. At times some people will just keep the usual notation but put a W here to say that xn converges weakly to x. So strong convergence will be, let me highlight that also. So strong convergence will be emphasized by xn converges strongly to x. So this means norm of xn minus x goes to 0. Okay, good. So now let's take some characterization of an implication of weak convergence and strong convergence. Which one implies the other one, and what are the properties of weak convergence? So proposition 3.5. So let xn be subset of a sequence of elements of, so let xn, right, sequence of element of E, right, then you have the following property. Say number one, it's called A. So strong convergence implies weak convergence. So if xn converges strongly to x, then xn converges weakly to x. So number two, so if xn converges weakly to x, then it is non-bounded, right? Then the sequence of norm of xn, so this sequence is bounded, and the norm of x is less or equal than the lim inf of the norm of xn. And number three, final property, if you have a sequence xn that converges weakly to x, right, and then you have another sequence fn of linear bounded operator that converges strongly to f in E star, right? Strong convergence here means the operator norm of fn minus f in E star goes to 0. Then fn, the sequence fn of xn converges strongly to f of x. Okay, let's prove this result. Proof. Okay, the proof is it's quite easy. I'm actually wondering whether I should write the proof down or not. I think I will skip that. So the proof is it's easy. So I leave it to you to to write it down. So maybe let me just kind of maybe write the outline of the proof, right? For the first one, the first one basically follows by continuity, right? So you want to show that, if I have some convergence, then the sequence also converges weakly. So it basically follows by continuity. So follows by continuity of f in E star. In fact, you just have this minus by continuity. This is less or equal than the norm of f times the norm of x and minus x. But by assumption, this actually goes to 0. But this fact is also clear from the fact that the weak topology is actually weaker than strong topology. So basically, you don't even need to write too much about the first property. So for the second property, number 2. So the second property basically follows from the uniform boundedness principle, the Banach-House theorem. So it follows from since for every f in the dual space, since for every f in the dual space, this sequence, the sequence of fxn is bounded, right? You have that, taking the limit, if you take the limit, taking the limit in this inequality, fxn is less or equal than norm of f times norm of xn. So if you take the limit, so this yields. So here I'm trying to prove that the norm of x is actually less or equal than the limit of the norm of xn. So basically the first point of this second property, as I said, followed by the uniform boundedness principle. So this yield, if you take the limit, remember f is continuous, absolute value is also continuous, so this yield, so oops, this will become x, so this is less or equal than times the limit. And then now you use the fact that, so this means, remember the norm of x is nothing else than the supremum of the absolute value of f of x over the f in E star such that norm of f is less or equal than 1. So this will be less or equal than the lim if. Good. So second point is done. Right. So for the third point, the third point is basically triangle inequality. So number 3 follows from the triangle inequality. Indeed, you have fn xn minus of this is less or equal than, you introduce a new point and then you remove, so it's actually nothing complicated. So and then you use the continuity properties. Oops, norm of xn. This is by continuity basically, so nothing. And here, you don't even need to do anything special here, because here we can use the assumption that this actually goes to 0 because xn converges with to x, and here we also have the assumption that this goes to 0, right? As fn converges only to f in E star. So then we are done. Okay, good. So now, well, it is actually noteworthy to mention that, in finite dimensional space, the weak topology and the strong topology actually coincide. So proposition 3.6. So when E is finite dimensional, looks a bit weird. It's finite dimensional, right? So the weak topology sigma E star, and the strong topology, or the usual topology if you want, the strong topology coincide. In particular, a sequence xn converges weakly if only if it converges strongly. So in particular, put it in this column. Sequence xn, right, converges weakly, say to x, if and only if xn converges. So you have an equivalence, converges only to x. Okay, proof. So let's have a proof of this. Proof. So we will denote by tau the strong topology. So let's denote by tau, right, the strong topology or the usual topology. So we want to show, it's always good to write what you are trying to show, right? So you don't get lost. So we want to show that the weak topology coincide with the strong topology. So you have a kind of equality. Okay, good. So we already have, as I said before, we already have sigma E star less or equal than tau. But please understand this less or equal as finer or coarser than. Finer than. So we know already that the weak topology is finer or weaker than the strong topology, right? So you already have sigma E star finer than tau as the weak topology always and always has fewer open sets than the song topology. Good. So now it is enough for us to check that. So it is enough for its surfaces order. Surfaces to check that tau is finer than the weak topology when E is finite dimensional. So that means you have to show that every strongly open set is let me find the color. Just write it. That means you have to show that every strongly open set, right, is weakly open. So this is what you have to show in order to conclude that both topologies coincide. So let x0 be in E, right, and U be a neighborhood of x0, I mean the strong topology. Right. So in order for us to show that U is actually a neighborhood of x0 in the weak topology, let me write it. Hold on. So we have to find. So we have to find a neighborhood V of x0 in the weak topology. In the weak topology, E star, right, such that V is contained into U. So this is what you have to do in order to conclude. So you want to find a neighborhood V of x0 in the weak topology such that V is contained into U. Because in that case, we will conclude that U is actually a neighborhood of x0 in the weak topology, and then we are done. So to be even more precise, let me write it. So in other words, so we have to find, because finding a neighborhood V of x0 comes back at finding finite collection of linear bounded topology. In other words, you have to find, because remember, we actually characterize basis of neighborhood of a point x0 in the weak topology. So we have to find say f1, f2, just to be consistent with what we've been doing so far. Fk in the dual space, right, and epsilon positive, such that V defined to be a set of x in E, such that Fi of x minus x0 is equal to epsilon for every I moving from 1, such that this V is contained into U. Okay, good. So fix are positive, right? Such that the ball around x0 radius r is contained into U. So just if you add those, just know that. Oops, trying to such just for your understanding, such and R exists, right? As U is a neighborhood of x0. So now what you do is that you pick a basis. So pick a basis, because remember E is finite dimensional. So pick a basis E1 up to EK, right? In E, such that the norm of EI is equal to 1 for every I. So therefore, by basis definition, so therefore every x in E can be written as x. This is the summation of the xi, ei, I moving from 1 to k. And now we define the map and define the map fi basically as a projection, right, from E to R. So fi of x equal to xi. So for every I, fi is a linear bounded operator. This is obvious, right? So moreover, we have the norm of x minus x0, right, is equal to the summation. Here we are going to use the 1 norm, right? So this is the absolute value of the sum of the absolute value of the component of the vector x minus x0. So we write this, right? So but this can be rewritten again as the summation by definition of the fi as x minus x0, right? So now this will be actually less than k times epsilon, right, for every x in V, because every x in V fulfill this slightly less than epsilon. So this means if you choose epsilon to be r over k, so choosing epsilon to be r over k yields that V is actually contained first of all in the ball, right, which is contained into U, and then we are done. So this is V contained into U, and we are done. So in finite dimensional space, the weak and the strong topology coincide. So remark, let's have a remark. So open set in the weak topology are always open in the strong topology. So open, restrictively close, like close sets in the weak topology. sigma e star, put it in column, are always open, respectively close in the strong topology. So, but in infinite dimensional space, the weak topology is kind of, it's weaker than the strong topology, as I said before. So, in any infinite dimensional space, let me highlight infinite dimensional. In infinite dimensional space, the weak topology is coarser, finer than the strong topology. So this means basically that there exist open, respectively close. We have an example, respectively close sets in the strong topology. That are not close, that are not open, respectively close, that are not open, respectively close in the weak topology. Good. So let's have an example, right? Example one. So let's see an example of such open set or closed set. So example one. Example number one. So consider the unit sphere. Consider units here. Let's define to be those are the x in E, such that the norm of x equals 1. Of course, with E, infinite dimensional, with E, infinite dimensional. Good. So the units here, the units here in infinite dimensional space is never close in the weak topology. Put it in color, it's never close. It's never close in the weak topology. It is obviously close in the strong topology, right? But never close in the weak topology. Sigma E star. So more precisely, we have more precisely, we have call it 1, because we are going to prove it. We have the closure of the units here in the weak topology, sigma. It's actually the closed ball, right? So this For this case, this is a closed ball. Close unit ball, close unit, just like unity, good. So, proof. So we start first by showing that. So let's first. So let's first check that this ball, no, call it B. Yes, B E 01 is actually contained into the closure of S in the weak topology. So let's first check this. So this means we want to check that, that for every x0 in E, right, such that norm of x is less than 1, x0 belongs to the closure of S. So indeed, so let say V be a neighborhood, the neighborhood of x0 in the weak topology, of course, because we want to show that x0 is actually in the closure of S in the weak topology. So we have to show, we put it in quotation mark, so you have to prove that V intersected with S is non-empty. Okay, good. So in view of proposition 3.4, because we know how to characterize neighborhood of x0 in the weak topology, so in view of proposition 3.4, let me highlight that so you can always go back and check. So in view of proposition 3.4, we may always assume that V has the form, this is a set of x in E such that absolute value of the dual pairing x minus x0 is less than epsilon, right? For every I moving from 1 up to k. Okay, with epsilon obviously positive, right? With epsilon simply greater than 0, f1, fk being linear bounded operators. So now let y0 belong to E. Let y0 belong to E, right, such that y0 is different from 0. Such that fi of y0 is equal to 0 for every I. Good. Well, you might be wondering whether such a y0 exists, but it is actually the case. Say, in quotation marks, such a y0 exists, right? Because otherwise, the map phi defined from E to RK, right, which is X associate phi of x equals to this vector of fi of x, I moving from 1 to k. So otherwise this map would be injective. Right, and phi would be an isomorphism from E onto the image of E, right, which is a subset of Rk, and thus, because phi is an isomorphism, the dimension of E would be equal to the dimension of the image space, right, which is obviously lesser equal than k. So which contradicts the assumption that E is infinite dimensional. Well, this proof is a bit constructive, right, but not really difficult. So such a y0 exists. Now let's define another map D, defined from R plus to R, which at T associate D of T equals the norm of x0 plus T y0. Obviously this function is continuous, so this is continuous on R plus, right, with observe that D of 0 is nothing else than the norm of x0, which is by assumption slightly less than 1, right, and J is actually goes to infinity, it's coercive, and T goes to plus infinity, this is equal to plus infinity. So from these two properties we can conclude that there exists a point t0 where d of t equals 1. So there exists, so hence there exists t0 positive such that the norm of x0 plus t0 y0, let me drag it first just to be a bit more clear, such that d of t0 defined to be this is equal to 1. So this means x0 plus t0 y0 is an element of V intersected with S. Good, and this basically ends the proof, but I mean this is obviously an element of the CR, right? Because the norm of x0 plus t0 y0 equals 1, but it's not clear that it's an element of V. So this belongs to V, right, as this dual pairing Fi at x0 plus t0 y0 minus x0. So this is equal to t0 of Fi y0, but this is equal to 0, right? Because we saw that we constructed y0 in such a way that Fi y0 equals to 0 for every I, and this is obviously strictly less than epsilon. So thus we have established that the CR is actually contained to the closed unit ball, right, which is contained to the closure of S for the weak topology. So now we are basically done, right? So in order to complete the proof, we just need to show that that the unit ball is actually closed in the weak topology. So let me write it. So in order to complete the proof, if we say the proof of 1, we just need to know that the closed unit ball is closed in the topology, in the weak topology, sigma E star. Indeed, we have, this is very easy to see, indeed. You can write the closed unit ball in E as the intersection over linear bounded operators such that norm of f is less or equal than 1 of a set of point x in E such that the absolute value of f of x is less or equal than 1. Let me shift it a bit. Good. Well, I think, how do we see that? It's actually really easy. So remember that the norm of x, right? Take an element in the unit ball, so the norm of x is less than 1. The norm of x is again the supremum of the absolute value of f of x, right? Where the f in E star such that norm of f is less or equal than 1. So if this is less than 1, so but this, basically implies that, so this basically implies that, or it's even equivalent to the fact that all the elements, all of these things are, so this is less or equal than 1 for every f in the Joule space such that norm of f is less or equal than 1. And then you're basically done. So B is equal to the intersection, right? So which is an intersection of weakly closed sets. Okay, good. So we know that, we just had an example of a closed set for the song topology, which is not closed for the weak topology. Now let's have a look at an example of an open set for the weak topology, which is not open for an open set for the song topology, which is not open for the weak topology. So example number 2. So the unit ball, put it in color. So the unit ball, say U, just to make a difference. U set of x in E such that norm of x is strictly less than 1. If E infinite dimensional, let me highlight that. Again, this is never open. It's never open in the weak topology. Good. Well, the proof is rather straightforward, I would say. So, indeed, assume by contradiction that it is open in the weak topology. That U is weakly open. We write it here. It's weakly open. Then its complement. So U complement, right? Which is basically the set of x in E such that norm of x is greater or equal than 1. Then this is weakly close. So it follows that. So therefore, it follows that. So it follows that the units here, which is basically the intersection of the closed unit ball and the complement of U, right, is also weakly close as finite intersection of weakly close as intersection of closed subset. No, of weakly closed sets. But this is obviously a contradiction by example 1. So this is contradiction, or rather this contradicts example 1. Okay, good. So, and then we are done. So, I think let's have another remark. In infinite dimensional spaces, the weak topology is never metrizable. So there is no metric. There's no metric on E, right? That induce on E the weak topology. So remark. In infinite dimensional, let me write it. So in infinite dimensional spaces, the weak topology is never metrizable. So there is no metric you can put. It's never metrizable. So this means there is no metric for theory norm right on E that induces on E the weak topology. But as we will see later, if the dual space is separable, then we can construct a norm on E that actually induces a bounded set, unbounded set of E, the weak topology. But this is actually feasible. However, let me just write it. So however, as we shall see later, if the dual space is separable, one can construct, it is possible, one can construct a norm in the space E, right, that induces unbounded set bounded set of E, the weak topology sigma E star. Okay, so second remark. So there are infinite dimensional spaces, with the property that every weakly convergent sequence is strongly convergent, like the L1 space. So there are infinite dimensional spaces, right, with the property that every weakly convergent sequence is strongly convergent. As an example, you have the L1 space, right, the space of sequences, such that this series converge. Let me just write in. So the L1 has this that, say, unusual property. Well, you might feel a bit confused, but let me kind of make things clear. So this does not actually contradict the fact that in infinite dimensional spaces, the weak topology is strictly coarser than the strong topology. So this fact, let me write it. So of course, this fact does not contradict the fact that in infinite dimensional, we highlighted infinite dimensional spaces, the weak topology, another column, so the weak topology is strictly coarser than the strong topology. Well, this is due to the fact that maybe, in fact, what you should keep in mind is that, if you have two metric spaces with the same convergence sequences, then, they have identical topology. But if two topological spaces have the same convergence sequences, they don't need to have identical topologies. So, I think that was a bit too fast. So let me write it. Indeed, why does that do not contradict? If I keep in mind that two metric spaces, let me write metric spaces, it is important. Two metric spaces or metrizable spaces, if you want, two metric spaces with the same convergent sequences have identical topology. Right? But, however, if two topological spaces, if put it in color, if two topological spaces have the same convergent sequences, they need not have identical topology. Topologies. Good. I think this is clear enough. And with this, we end this video. Right? I hope you actually enjoyed the video. And again, if you have any questions, feel free to leave your thought in the comment, or you can also reach out to me via email. Yeah. So thank you once again, and see you in the next video.